Hello Chem 1B, this is our solution chapter, video 8, and we're going to be talking about two new colligative properties, boiling point elevation and freezing point depression. Now for boiling points, when we add a solute to a solvent, the boiling point of the solvent will increase. And we need to go over why, because you should know why this is happening. Now, we know from our previous videos that the vapor pressure will decrease when we add a solute to our system. Now, boiling point, if you don't remember from Chem 1A, a boiling point is when the pressure of our vapor pressure of our solution or substance is equal to external pressure. And if our vapor pressure decreased, then we have to heat up the solution even more to get its vapor pressure to be equal to the external pressure. So we're going to need to heat up the solution even more to get that vapor pressure back up to the external pressure. Now for a normal boiling point, when we see the word normal, this is very important. This means that our external pressure is 1 atm. Now, quantitatively, so if we want to actually calculate what the new boiling point is of a solution, we use this equation, which is our boiling point elevation equation. Now, it relies on three different variables to calculate it. It is important to note, though, that this equation does not calculate the true boiling point. It calculates the change in our boiling point. And we'll talk about in a second how to get the new boiling point from that change. So it relies on three variables. I, which is our Van't Hoff factor. And so the Van't Hoff factor is based on the solute. We talked in a previous video about how to determine the Van't Hoff factor. Kb, which is a constant. And so the constant does depend on your solvent. So if you have a different solvent, then you'll have a different Kb value. But otherwise, it is a constant, it doesn't change. So for water, for instance, the Kb value is 0.52 degrees Celsius per molality. And that's always the value for water. But if we're dissolving our solute in a different substance other than water, then the Kb value would be different. The last term that is going to be important in this equation is the molality. It is our molality of our solute. So we learned in previous videos of this chapter how to calculate molality, and now we're going to use that and apply it in this equation. Now, once you have the Van't Hoff factor I, the constant, and the molality of your solution, you can calculate them together to get your change in your boiling point. Once you have that change in the boiling point, we've calculated our delta TB, we can calculate our new boiling point by adding delta TB to the original boiling point of the solvent. So for instance, water has a boiling point, pure water, of 100 degrees Celsius. If I knew delta TB was 5 degrees, then my new boiling point of water would be 105 degrees, because I'd take my original boiling point, 100 degrees Celsius, and add my delta TB to it to get the new boiling point of my solution.
Let's look at freezing point depression before we actually do a calculation. Freezing point lowering or freezing point depression is defined as a decrease, right? Depression, lowering. As we add solute, our freezing point of our solution is going to decrease. And quantitatively, the equation looks identical to the boiling point equation. This is our change in our freezing point of the solvent. This is our Van't Hoff factor again. And we have our freezing point depression constant, and we have our molality of our solute. These two properties are super important to a lot of different practical applications. For instance, coolants generally are a mixture. If you've ever refilled the coolant in your car's radiator or in your coolant system, you're going to be mixing ethylene glycol, antifreeze, with water in a 50-50 ratio generally. And the reason why for that 50-50 ratio is because it increases the change in the freezing point and the change in the boiling point at their maximum points, so that we have a very large area that our coolant remains a liquid. This is also why we salt our roads in cold areas of the country to prevent ice from forming. What happens when ice forms on a road is generally due to it raining or snowing the day before. And during the day, that water stays in the liquid state. If it snows on the road will melt the snow because it's hot. We have cars driving over it. It's black. It absorbs heat from the sun. But at night, all that water freezes. Why? Because it got cold enough to get below the freezing point of the water. But if I add salt to the road, I increase the molality of the solute in my equation here. Delta T goes really high. And what this means is our freezing point goes so much lower that even though it got really cold at night, it didn't get low enough in temperature to freeze the water, because it's not just pure water anymore. It's pure water with salt in it. KCl is generally the salt used in salting roads. It's kind of neat. Anyways, so let's talk about this a little bit more, right? So what happens when we add a solute to a solution is that both the boiling point and the freezing point expand the region that the liquid state is present, right? So our boiling point increases to the red line here. Our freezing point decreases to the red line here. So this whole area now is where our substance is in the liquid state. Whereas before, it was just in the blue area, right? So I'm trying to do it with colors. So before we add the solute, our liquid state is just in this blue region. But as soon as I add that solvent, it's that region plus this area is as well going to be liquid state for our solution. Type scenario. Again, this is due to the fact that as we add solute, our boiling point increases, our freezing point decreases. And when this happens, both the solute is excluded for both the solid and the vapor phases. We need more heat available to get those liquid molecules to escape past the solute for the boiling point, and we must cool the liquid even more so that the liquid molecules can freeze and form a solid crystal structure. So let's do some calculations. We have our 35% mass of ethylene glycol mixture. Ethylene glycol, if you remember, is C2H6O2. And we want to calculate the freezing point of this solution. So in order to do that, I'm going to assume, again, same as last time, that I have 100 grams of solution. This tells me that I have 35 grams of C2H6O2. Now, according to my equation, delta TF is equal to I times KF times my molality. Ethylene glycol is this guy. It's a non-electrolyte. So I equals 1. And KF is given. It's right here. We need to calculate molality. So I need moles of ethylene glycol. Which is 62.08 for the molar mass. So we divide by that. And this gets us 0.564 moles of C2H6O2. Molality is moles of solute over kilograms of solvent. So I need the kilograms of solvent. I know that I had 35 grams of solute and 100 grams of solution. So this means I have 65 grams of solvent, which means I have 0.065 kilograms of solvent. So I put my 0.6564 moles up top, and I put my 0.065 kilograms in the denominator, and I can get that my molality is equal to 8.68 molal. This value I can plug in there. So my delta TF here is going to be equal to 1 times KF 1.86 times my molality 8.68. And if I do all that out, I get 16.1 degrees Celsius. This is not my freezing point of this solution. It's the change in the freezing point, delta TF. So I need to figure out what is the new freezing point. That's what I was asked for in the problem. I know that the freezing point of water by itself is 0 degrees Celsius. For this solution, it changed by that, 16.1. So my new freezing point of solution will be equal to 0 degrees Celsius minus 16.1 degrees Celsius, or in other words, negative 16.1 degrees Celsius. All right, so let's do one more example. Same equation, just now boiling point. We have delta TB is equal to I times KB times molality. And we're using the same solution, so our molality is still 8.68 molal. But our KB is different than our KF, and I is still 1 because ethylene glycol is still a non-electrolyte. So let's plug in. Delta TB is equal to 1 times 0.52 degrees Celsius per molality times 8.68. Molality cancels. We're left with degrees Celsius. This gives me a freezing point or a boiling point elevation or a change in our boiling point of 4.5 degrees Celsius. Again, this isn't our new boiling point. Remember, boiling point elevation, we're increasing our boiling point by this much. And we know the original boiling point of water is 100 degrees Celsius for pure water. So my new boiling point is going to be equal to 100 degrees Celsius plus 4.5 degrees Celsius, or 104.5 degrees Celsius. All right, so if you have any questions about any of these colligative properties, please let me know. I am very quick at responding to email these days, and I have my office hours available as well. So if you have questions, just let me know.